So I think the question you're talking about is this one right here.
Yeah.
Minimize, find the minimum amount of fencing needed to enclose a rectangular area of 9,000 feet. So it's just a simpler version of the one that I did. So you just have a rectangular area. And so the fencing that you need is twice the length and then twice the width. All right, so let me see if I can get a little bit of annotation going up here. So that's the formula for the fencing needed. And then it has two variables. And since we want to find the minimum, we're going to have to get the derivative of the fencing, right? So we need to get rid of one of those variables. And remember, I told you when you have these problems, a lot of times the physical problems will end up having two variables or more sometimes. And you have to find other ways to substitute out one of the variables in terms of the other, some kind of relationship. And that's what this area equals length times width. And then so 9,000 square feet equals length times width, and we divide both sides by length, and we end up with this substitution for width, which is what gets put in here for W. Okay, and then at that point, it just becomes, writing, kind of simplifying this and writing the L that's in the denominator as L raised to the -1, so that then we can take the derivative. And then we set that equal to 0 and we solve. And once we get that, we have to make sure that's just a candidate. So we need to take the second derivative. I just happen to solve this using the second derivative test. So the second derivative is 36,000 over L cubed. And when I put in a positive number into that, I get a positive out of it. So it's concave up, so it's a minimum. So that means that I've now found the minimum length. That doesn't answer the question. So I'm going to go put that up in here and get the W. And now I have the W. And once I have that minimum W, I have to go back and read the question initially and make sure I answer the initial question. It says, what's the minimum amount of fencing? So I need to go back to my fencing formula and substitute L in and W, and then finally I get the answer. Okay.
Okay. Thank you.
You're welcome. Does anyone else have another question from this homework before I stop sharing? So what's the next question? What we want to do here is use the instantaneous rate of change to find, we want to find the instantaneous rate of change when you use it, do it with the limit. So what we want to remember is that the instantaneous rate of change, and if I happen to start writing too small, somebody call me out, remind me, okay? So it's the limit. So that's what this LIM means, right? The limit as H goes to 0 of the average rate of change. So I'm going to come up here and I'm going to draw like a little pretend drawing. We've seen this drawing before, where we have 2 points. I'm going to call this one A, and it's at X. And this is the function F, let's say. Let's say it does some crazy thing. This is F. So this is X, and this is F of X is the height. We got some other point B, and it's at X plus H. So we have a distance on the X-axis of H. And the height, so the point is X plus H is the X coordinate, and the height is F of X plus H. That's the Y coordinate. So this is like X2, and this is like Y2. Okay. So now the average rate of change is the slope. Oops, there I go, writing small. So the slope between those 2 points. slope between A and B. So all we're going to do is we're going to put a line between A and B, and we're going to get the slope of that line. So that's going to be the limit as h goes to 0. So this part we're just writing, it comes along for the ride. So the slope is the rise over run. So it's going to be the y2 minus y1 over x2 minus x1. All right, so what is that? Well, I'll write it down here below. So this is equal to the limit as h goes to 0. So what's y2? Y2 is the height on the b function. So that's f of x plus h. So all this part, you guys already have hopefully memorized that this is f of x and that's y minus y1, which is the height of the first point A. And then the whole thing goes over h because it's the run, which is just h. So the distance between on the x coordinate between x and x plus h is h. So that's the run, rise over run. All right, so that's the formula we're going to be working with to get the instantaneous rate of change. All right, so now that was sort of a review of the where it comes from. Now I'm going to actually plug into this formula. And we're going to obtain, and let's see if I can get my color on here. Can you guys see the green okay? I'm going to get that this function is going to, instead of being evaluated at x, it's going to be evaluated at x plus h. So let's go ahead and get that. So f of x plus h. What I was saying is that the instantaneous rate of change is the limit as h goes to 0 on that average rate of change, which is the slope between the 2 points. And that's just rise over run, y2 minus y1 over h2 minus h1, and then that's where this formula comes from. All right. So this formula was, so arriving at this formula is really just a review, okay? All right, so now I'm going to actually apply that formula to this function. So I'm going to get f of x plus h. So everywhere that there's an x, I'm going to replace it with x plus h. So this is going to be 5 times x plus h squared plus 2 times x plus h minus 7. Okay. You guys see that okay? Is that all right? Okay, great, good. All right, now, this now just becomes algebra, but there's a little bit of a gotcha algebra step here that a lot of people get messed up on. And that's this x plus h squared. You can't say this is x squared plus h squared, that's wrong. You actually have to say this is x plus h times x plus h. All right, that's what this x plus h squared is. And the only way to actually solve this is to FOIL it out. Now over here, we just have a coefficient in front of these parentheses so we can distribute that. That's okay. So that's 2x plus 2h. And then we have the minus 7. All right. So I'm going to erase this part down here. Is it too tight for me to write in here? Can you guys see what I write in here? If I say this is 5 times, and I FOIL this out, I get x squared xh plus xh plus h squared, and then plus 2x plus h minus 7. I'm going to erase this. I think I need a space. Can you guys see that okay? Was that too small? Is that all right?
It's fine.
Oh, good. Okay. Okay. Hold on. Now my recording, my initial recording for my other thing is trying to ask me where to store it. Give me 1 sec. I'm just going to put it in the desktop. All right. All right, so the next thing that we want to do is go ahead and distribute this 5 throughout everything in here. And by the way, these are like terms, so we have 2 of them, 2xh. So we're going to distribute the 5 inside this parentheses, and we're going to get 5x squared plus 5 times the 2 of like terms here, so that's 10xh. 5 times this h squared plus 2x plus 2h minus 7. Right. Now there's no like term, so this big giant mess is what f of x plus h comes out to be. So now we're going to subtract f of x from this. That's what this says. Take f of x plus h, which we did. That's this big giant mess. And then we're going to subtract f of x. So we're going to subtract f of x means we're going to subtract f of x squared. And I can put put parentheses around it, I guess. And we have plus 2x. And we have a minus 7. So we're going to distribute this negative now throughout. So we have 5x squared plus 10xh plus 5h squared plus 2x plus 2h minus 7. And we're going to subtract 5x squared. So now I'm distributing this negative in here and in here, minus 2x. I'm going to put it under like terms. And minus times a minus 7 is a plus 7.
I'm just a little bit confused where you got the minus f of x. Could you just repeat that one more time?
So what I'm trying to do is get that average rate of change formula, right? And it was f of x plus h minus f of x. So I'm just working on that part of it. And then we're going to
okay.
h.
All right, thank you.
So all I'm doing here is I'm subtracting off the f of x. So I should put maybe a colon here. Like this is like what I'm doing. So now this part right here is, let's see if I can go ahead and squeeze this in here. This is the numerator part of this. Just the numerator, f of x plus h minus f of x is what this is. This is equal to this. So we have the f of x plus h minus f of x. Okay? Now I need the space, so I'm going to have to erase this. I'll try to write it down below. So that area, the average rate of change is going to be f of x plus h minus f of x over h. So let's go ahead and simplify this. This is the f of x plus h minus f of x part. So we'll cross those out. We'll cross these out and we'll cross that out. And what we're left with is 10x plus h, 10xh, sorry, plus 5h squared plus 2h. And then that whole thing is divided by h. So in the numerator, I'm going to factor out an h from each of these terms. And I'm going to get h times 10x plus 5h plus 2 all over h. Okay? Okay, so if everybody's good with all that, I'm going to divide out the H's now, cancel those out. And I told you, when you do the average rate of change using this formula, where we take the average, y2 minus y1 over h, the h is always going to cancel out. Okay, and so we're left with that the average rate of change. Now I'm going to write it up at the top because I need more space. All right, so now that we have the average rate of change, so the average rate of change is, the h is canceled, is 10x plus 5h plus 2. All right, so now that we have this, the instantaneous rate of change is the limit when h goes to 0 on the average rate of change. So that's just saying we're going to put the limit as h goes to 0 of this, 10x plus 5h plus 2. And all that means is that wherever there's an h, we're going to put in 0 for that h. So all that means is we got 10x plus 5 times 0, because that's where the 0 is, plus 2. So what we're left with is 10x plus 2. All right. Now, our original function here was 5x squared plus 2x minus 7, remember? That was the original function. Now, using the power rules for derivatives, we can just take the derivative and we say this is 5 times 2, or 10x plus 2. So we can confirm really quickly that all the work we did through this more complicated, long way of arriving at the derivative does match. Right? 5 times 0 is 0. Any questions on that? How that worked out for us? That was a good choice of a good first question, by the way. Anything, what's the next question? Who would like to see?
I have a
Something.
question about this.
Yeah.
How would this be worded if you were to ask for this on an exam? Like, what's the easiest way to look out for this problem? Just because I don't know how it would be.
Okay. It would say, I'm going to try to write it out so you kind of see it in writing. So I think what it would say is something like, use the limit definition of the instantaneous rate of change to find either the instantaneous rate of change or the first derivative. So it would have to say something about using the limit definition, or maybe it could say use the limit as h goes to 0 of the average rate of change to find the first derivative, something like that.
All right, thank you.
Sure.
Hey, I have a question.
Great.
Can you talk about tangent lines and how to find them?
The tangent line, sure. So if you're asked to find the tangent line, that's a little bit of a more complicated question, but that's a great question. So you would have to have a place where you're finding the tangent line. So if you're told to find the tangent line to F, let's say, at, and let's say we have a specific place. So let's say we're asked to find at x equals, I don't know, 2. All right, we want to always have, if you're going to be having to find a tangent line, you have to find it at a place. So that would have to be part of the question. So we want to find the tangent line to the function at x, f of x, at x equals 2. Well, to find the tangent line, a tangent line is always going to have the form, because it's a line, y equals, and I'm going to put a little capital T as a subscript since we know we're trying to find a tangent line. It's going to have the form y equals mx plus b. Okay, so the m from the tangent line at x is f prime. That comes from the derivative. Right, so the slope of the tangent line at x equals 2. So remember that m, and I'm going to put a little m sub t here. So the tangent line is the derivative at 2. Okay, so we want to find the derivative at x equals 2, and that will be this, the mt, and then use the point, and the point is going to be 2 f of 2. So that's the x and the y. So remember, if you have a slope and a point, you can always get the y-intercept and get the equation of the line to get. Use point and the slope, and I'm going to do an example of this one, to get the b. So we want to use that to get this b over here. And then we would have the equation of the tangent line. So let's actually do one. Let's do an example of that. So to find the tangent line of a function at x equals 2, we just had this function. I'm thinking of whether maybe we want to do a different function just to practice derivatives. Does anyone have a derivative they want me to do that I can use right now? I'll go ahead and think of one that involves a chain rule so we can practice that. How about if it's 3 times 2x plus 7. Let's say, hold on, instead of 3, let's come up with something. Maybe how about 4/3 cubed. All right, let's say that's our function. I hope I'm not getting myself into a big mess here, but okay, let's just say this is our function. And so we want to take the derivative of that, because we want to find the tangent line at x equals 2 for this function f of x. So we're going to get the derivative at 2. So we need, first of all, we just need the derivative. So by the chain rule, we're going to bring this exponent down, right? And you guys, I'm not blurry, right? Everybody's good. You can see this. Is it coming across a little bit better now?
Yeah,
No,
it's
you're,
good.
you're good.
Good. Okay. So we take the coefficient 4/3 and we're going to multiply by the exponent 3. And then we're going to take what the inner function is, this 2x plus 7 that just comes along for the ride. And we take 1 off the exponent. So that's 2. And now we're going to, that was the outer wrapping of the gift. Now we're going to multiply by the derivative of the inside, which is 2. Right. So the derivative of 2x plus 7 is 2 times plus 0. So we just get a 2. Is everybody good with that? Let me just stop there because I want to make sure we're good with taking derivatives using the chain rule. So the outer function, so if I wanted to write this as a u of v, I would say u equals, all right, here, u equals 4/3. Let's say I want to write it as u of x, u of w. U of v actually. what am I thinking? Yeah, u of v. So it's 4/3 v cubed is what this outer function is. And then v of x is 2x plus 7. So we take the derivative of the outer function, that's 4/3 times 3v squared, and then we multiply by the derivative of v, which is just 2. Okay. Any questions on that, or I'm going to start simplifying things?
You kind of lost me there. I don't know if anyone else is a little confused, but
Okay, so what part of the chain rule is losing you?
where you did the u of v, once you started that part.
Oh, this, you don't have to do this.
Oh, okay.
You can, if you're following the chain rule up here,
Mm-hmm.
you can ignore all this. This is just for people who aren't seeing it as an outer and an inner function yet.
Oh, okay. All right. Thank
Are you following this part up here?
you. Yeah, that part I got it.
Okay. Any other questions on this part up here? Okay, so the 3's cancel. And then this 2 is on the outside of this parentheses squared. So I'm going to multiply it by this 4. So my final derivative is going to be 8 times 2x plus 7 squared. All right, so we got the derivative. We're all set. Now we got to get the, we were asked to find the tangent line at 2. So we need the slope at 2. So we're going to get the derivative at 2. So m of the tangent line is going to be f prime at 2, which is just 8 times 2 times 2 plus 7 squared. Let me erase this. And that's, so I just plugged that into this derivative formula, right? So that's 2 times 2 is 4. So it's 8 times 4 plus 7 is 11 squared. So I think I need a calculator for that. So 8 times 121.
Wait, where'd you get the 8 from? When it goes,
Because when I simplified it here, I got this 2 times a 4. So it's 4 times 2 if I just combine my numbers that are left. Okay? Okay?
yeah, thank you.
Okay. So now 8 times 121, I get 968. So that's my slope. My slope is 968. That's like super steep. That's almost vertical. Like, I think it would look really like vertical almost. All right, so now that we have that, we need to get our point. So our point is when x is equal to 2, we need f of 2. Well, that's the point 2, and then we're going to plug into this whole thing. So it's 4/3 times 2 times 2 plus 7 cubed. All right, so what is that? So that is the point 2 and C. I got 4 plus 7. I already know that's 11, but this time instead of squaring, it's cubed. So it's 11 cubed times 4/3. Okay, and I get 1774.7, let's just say. All right, hopefully you matched me. All right, so now that we have a point, so we got our slope, that was 968, and now we need to find b to get our equation of a line, of this tangent line. So we're going to plug in the point in here and solve for b. So I get that 1774.7 equals 968 times 2 plus b. This is the y equals m of the slope of the tangent line at 2 plus b. All right, so that's all that is. So 968 times 2 is 1936. So I'm going to subtract 1936 from both sides. And then simplifying this. So that's negative 161.3. And these cancel, and we're left with that equals B. So now I get that my tangent line to F at x equals 2 is given by y equals, and the slope was 968, x minus 161.3. Whew, that's a long problem. Okay. Good one, though, to review a lot of kind of the stuff from back at the beginning of the semester, too.
Yeah, and is this gonna pop up on the test?
Is this going to pop up on the test?
Yeah.
Well, I'm not going to say, but it might.
Okay.
Definitely the skills involved would pop up on the test. As far as finding, recognizing that the slope of the tangent line is the first derivative and that you have to go through and get that. In some sense, this is a really good final question, like a question for a final, because it's reviewing like everything. I don't know. I mean, not everything, but it's going back to remembering how to get the equation of a line.
Yeah, thank you.
Back from more earlier exam 1 material. So
Appreciate it. Thank you.
sure. Okay, so what's the next question somebody wants to hear about, or topic you want to see a question on?
Can we go over an inventory cost problem?
An inventory cost problem, yep. So if you remember, I told you, you're not going to have to memorize this, but the inventory cost is a function of, instead of a function of X, it's a function of quantity, which is the size that you're going to order. And what I told you was that there is an ordering cost. So let's say that ordering cost, and I think I was using P here for the cost of an order. And if you think of it, if P is the cost per order, then you got to multiply this by the number of orders. So let's say you have a demand D, you divide it by however many are in each order, which is the Q, and that's the number of orders. So together, this is the ordering cost, right? Then the other part of this that we talked about was the holding cost. And for the holding cost, we talked about the average inventory in the warehouse. So it's however many you order divided by 2 is the average that's usually in there, times the cost per unit to put it in the, to keep the cost per unit per year to keep it in a warehouse. So it's cost per unit to store it. And so this is the storage cost, or what some people call the holding costs. Together, these are the pieces that we need. Again.
After the
Go ahead.
Q over 2, is it a plus H or?
No, it's multiplied. So this is, think of Q over 2 as being how many you got to put in the warehouse. And then this is the cost per each one that's in the warehouse. But the amount that's in the warehouse is going up and down throughout the year because you're putting stuff in the warehouse, you're taking it out. So this is the average cost. This is a simplification of a very complicated process. And when you get, if you were to get into a little bit more advanced operations type equations that you would maybe, if you were working in management and operations and you were like running warehouses, it's also probably part of supply chain. You would probably get more complicated than just taking the average. You would come up with some function that changes, but we're not doing that. We're just introducing this topic. I'm not even requiring that you memorize this formula. I just want to introduce it as a situation in business where you can take, where a derivative can help you. All right, so when you get a problem like this, what you're going to want to look at is what is the demand. So look for the demand. So it'll somewhere you're going to get the demand T, and then also then the cost per order. Which will be the P. And then the next thing you're going to look, so you have to find these 3 bits of information in the word problem: the demand, the cost per order, and the third thing is the holding cost. Once you have those 3 bits of information, you have everything you need to build this formula. And then at that point, it's just taking the derivative, and this, because this formula has the same structure, it's the same derivative every time. The numbers change, but the actual, like what you do with the, to take the derivative. So why don't we go ahead and do one of these that I didn't do, okay? All right, so the one that I didn't do, I'm happy to go over. It says, so I'm gonna read it to you. It's on Brightspace, and you can look at it yourself. But as I read this, start looking for these variables to see which when we hit on them, we're just going to write them down. We're like, oh, I hit that one. I know that one. Now I know that one. Okay, so one retailer of smart televisions has an annual demand of 400,000 televisions. Ding, ding, right? Annual demand, 400,000. Okay, we got that number. Every time he places an order for Q number of TVs, it costs him $80. Hey, ding, ding, we have a cost per order. All right, next. It also costs the retailers $100 to keep one TV in inventory. So, we now have the cost per unit to keep it in a warehouse in inventory. So at this point, we're all set. Like these problems are, once you kind of realize those are the 3 variables you have to find, and that this is the formula, you don't have to have it memorized. I will give it to you. You just plug into that. Some people just call it I for inventory cost. I've been calling it IC, but hopefully that's not throwing you. It's just the name of the function. Like we call them F or G. Sometimes you can have a function name that has 2 letters, and that's okay. Just think of it like an F. So it's a function of quantity. Okay, so now we just put everything in. It's going to be 400K divided by Q, because this is the variable we don't know. This is like the X. And this is going to be multiplied by 80 plus Q over 2 times the holding cost, which is 100. All right, so once again, the structure for every one of these problems is the same. We have 1 Q in a denominator and the other Q's in the numerator in this term. So let's go ahead and multiply this out. So we're going to do 80 times 400, right, which is 32 million. 400,000, sorry, 82 million. And I'm just going to save one step. I'm going to do this one step. I'm going to do 2 steps in one. I'm just going to pull this Q up as a -1. You're going to do that every single time you have one of these inventory problems, because to take the derivative, we always take, when we have a term that's got a variable in the denominator, if it's possible, we can just pull it up by putting a negative on its exponent. That's the easier way to take the derivative. Okay, and then this 2, this is going to divide into this 100. I'm going to have 50Q. Okay. So let me stop there. Is everybody good with getting that equation?
Under the H at the original equation, it says cost per what? I can't really see it. I'm sorry.
In the problem, it said it's the cost. It also
No, where you wrote the equation for the whole thing. And on the whiteboard,
Yeah,
right there. Yeah, it says cost per something. I can't
per
remember.
unit, cost per
Oh,
unit.
okay. Thank you.
Yeah, let me see if I can. That's worse. So, sorry, I'm just trying to move this around so I get less glare. Is that okay?
Yeah, that's good. Thank you.
Okay. All right, so we're good. Everybody's good with getting to this point. So now the derivative, right, is the power rule. So we're going to bring that -1 down. So it's minus 32 million. And I'm just going to put a big M for million. Q to the -2 now, because I subtract 1 off, and then plus 50 times 1, and just 50. All right. So now I need to find my candidate for minimizing my costs. So I'm going to take my first derivative and I'm going to set it equal to 0. And I'm going to solve. So I get that minus 32 million. And I'm going to go ahead and put this Q back in the denominator so that I can solve for Q. So I'm going to bring that up under Q squared plus 50 equals 0. So the first thing I'm going to do is move this thing, make it positive, and move it over here. So I get 50 is equal to 32 million divided by Q squared. Then I'm going to multiply both sides. Oh, sorry, I know that's in the bad zone here. Does that help? Hey, I think I got rid of the glare. Is that looking better? Okay, well, no answer, but hopefully
Yeah, it
that's
does.
It's better. Okay, so everybody's clear on what I just was doing. I'm just doing a little algebra. I'm going to solve for Q squared. So now I'm going to multiply both sides by Q squared. And I'm going to divide both sides by 50. So I get Q squared is equal to 32 million divided by 50. All right. And that's 640,000. So to get Q, I got to take the square root of this. Now, technically, Q could be the positive or the negative square root, but because Q is a quantity and this is an actual business application, it's not realistic to have Q be negative. So Q is only the positive square root of 640,000. And that turns out to be 800. All right, so that's our candidate critical value. So now we have to go back and figure out if it's actually the minimum. All right, so let's do that by getting the second derivative. I'm going to go down here where the first derivative was, because that way I can just read it right off. So I got this minus 32, and I'm going to bring down this exponent of a -2. So minus 32 times the -2. And you could do that step in your head if you're comfortable. And then we're going to take one more exponent. We're going to make that a -3, and then the 50 goes away. All right, so what we're left with is minus 32 times -2, which is 64. And we're going to put this Q back down in the denominator by changing the exponent from a negative to a positive. So we have 64 over Q cubed. That's our second derivative. So that means I now have a tool that will tell me if any critical value is a minimum or a maximum, or neither. So I'm going to plug in this Q of 800 into that. So let's go do the second derivative test. So the second derivative of the inventory costs at Q is equal to the 64 over Q cubed. I'm just recopying it right here so we have it. So when I plug in the 800, all I care about, right, is if it's positive or negative. So remember, the second derivative is the concavity or the mood, if you will. So 800. Now, this is 64 over 800 cubed. Now, I don't care what that number is, right? All I care is if it's positive or negative. So the numerator is positive, and the denominator is a positive number cubed. Well, that stays positive. And any two numbers, when you have a positive over a positive, it has to stay positive. So this is kind of a happy function right here at 800. It's smiling, right? It's concave up. So that means if it's concave up, you got to have a local minimum, because remember, we already know that Q equals 800 makes the first derivative 0. So we know we have a horizontal tangent, but now we know it's concave up. So that means it's a local minimum. All right. So we have answered the question about what order size will minimize the annual inventory cost. So, but we haven't answered the question on what is the minimum inventory cost? Because, you know, if you're budgeting, you might want to know what that is. So now that we know that we have a local min, we need to actually find what that inventory cost is at 800. This is like the y coordinate. If you were going to graph this function of the inventory cost and have Q be the x axis, the values are the y. So we want to get this value here, and we're going to plug into this formula, right? The original function. So it's 32 million over 800. And plus 50 times 800. All right, and I barely have room here, but that comes out to be 80,000. So your minimum inventory cost, if you use an order quantity of 800, is $80,000. Okay.
Can you
got
repeat? I'm sorry. Can you repeat that last part? After you found out it was a local minimum.
Yes. So once I found out it was a local minimum, all that tells me is what the Q is. So let me maybe try and do a little bit of drawing here. So I don't know what this function looks like. It's some, whatever it looks like. It's Q, and we have some quantity. We could order all 400,000 in one order, and then we have a formula for the inventory cost, and it's some form function, and I don't have it graphed in front of me, but whatever it is, we know that it reaches a minimum. So this cost, whatever it is, reaches a minimum. You might do other things, I don't know, but at 800, right? That's what we figured out. But the actual inventory cost has to be the y coordinate. So we need to find out what that is. And the way we do that is we have to go back into the original function to get the y coordinates. And that was that original function we came up with using that d, the d, the p, and the h. And we came up with this formula right here. Okay, remember when we did that? So all I'm doing is plugging in 800 in this formula. So I'm getting the y coordinate of that local minimum.
When you did at the bottom, the second derivative, when you did -32 times the -2,
Mhm.
did it matter if you did the -32 million or
Oh,
you
good
just?
point. That was actually -32 million. That's 64 million. No, it doesn't. What matters is that the two negatives canceled and became a positive.
Mm.
Yeah, that should have been a 64 positive million. Thank you. Good catch. Okay, well, it's 6:07 and I have to cook dinner. So I need to go, does anyone have a last pressing problem they want to see me do?
Will you be posting this session, right?
Sure.
Okay, thank you so much.
Okay.
Do you have time to do one more, just a derivative of the natural base E?
Sure. I was
Okay.
hoping someone was going to ask me a derivative problem. So
Yeah,
I'll do that and then we'll wrap it up. Okay.
sounds good.
What's it look like, or can you go ahead and read it out to me, what you want to see?
I didn't have one specifically, but I can find one real quick. Hold on.
How about, I'm going to come up with one. G of t equals, I don't know, 7e to the 4t q minus 3t, something like that, maybe?
Looks good to me.
Okay. So this is just a number out in front. It's going to come along for the ride. This is e raised to a function. So the rule, I'm going to just write it over here to the side, is f is e to some function, the derivative is e to that some function times the derivative of that function, right? All right, so for us, g prime, and so we're going to take 7 times the derivative of this is just e to that same thing. We're just copying it. Remember, I told you that e raised to something doesn't care about derivatives. It's going to repeat itself. But the chain rule will get us to bring down now the derivative of this exponent. So this is 4 times 3, or 12t squared minus 3. And then we can take the 7 and we can distribute it in here. So we have 7 times 12. Oh man, I don't know that one. 84, I think. Yeah, 84 t squared minus 21, and that all is in parentheses around e to the 4t cubed minus 3t. That's all there is to it. Okay.
All right. Thank you so much. Have a good one.
All right, you're welcome. All right, bye everyone. I hope you get a good night's sleep.
Oh, I had a
Thank
quick
you.
question.
Thank
Sure.
you.
Where I couldn't find the equations we should know for the exam. Like, where are they on Brightspace?
Oh, I may not have put them. They're in the review from class. I went over everything you needed to know in the review from class.
Okay, got it.
Okay,
Thank you. Have a good day.
you too. Bye.